We start the webinar. Good day, everyone. Welcome to the webinar, AI-powered predictive maintenance for Airline. I'm Vivek Vij, your host of the webinar. The presenter for today's webinar is Sumit Agarwal, CTO, Findability Scientist. Sumit is a dynamic leader with 12 years of experience in creating and delivering innovative solutions using big data and cognitive solutions. These solutions have been deployed from various organizations across multiple industry verticals and across business functions. Before we start the webinar, I would like to remind you of a few pointers. All the attendees will be on mute mode. You may type in your questions anytime during the webinar. Answers to all your questions will be taken at the appropriate sections or at the end of the webinar. Now I would like to invite Sumit to take over the webinar. Over to you, Sumit. Sumit, may I request
Thank you, Vivek, and good morning to thank you, Vivek, and good morning to all the participants. Before I start, a quick check, Vivek, can you hear me well and you can see my screen?
Yes, Sumit, I can hear you clearly, and we can see the screen. Findability Sciences is your photograph.
All right, thank you. So today's topic, we will discuss about how we are using the AI technologies to solve the predictive maintenance problem in the transportation industry. Before I start with the how we are using the technology or how these technologies can solve the problem, I would like to spend few minutes just to share with you how the whole AI thing works and the market is changed with the way machine learning and self-learning systems are providing the solution which was impossible if we think like 10 years before. Just to tell few quick points about my company, Findability Sciences. We are a big data, cognitive, and AI company. We started around 8 years before. We have developed a findability platform, which is a big data cognitive system by unifying structured and unstructured data, and then using these self-learning algorithms, machine can drive the models or the patterns from the data, so it can provide the predictive maintenance by telling you in advance where the problem may occur and when the problem can occur and what could be the solution. We serve many industries. Today we are focusing on transportation industry and one specific solution about predictive maintenance from many solutions our company offers. We are partner with IBM Watson, leading partner with IBM. SoftBank, if you heard the name, in US, this is the company who overtook Sprint. They are the investor in our company, and we have also found a JV with SoftBank. Quickly starting with when I told you about AI and how these technologies work today and how we utilize these concepts in the predictive maintenance, I would like to spend few minutes to tell you how this all evolved. So if we clock back for around 10 years and go back to 2007, you will notice probably in the computing world, that was the most important year ever. That was the year where the power of computing got into everybody's phone. The iPhone you have today is actually has more power in your hand than the computing power we had when we sent the first person to the moon. So the computing power, the amount of data we can process, the amount of capability for the machines, so we can write the algorithms that it can learn, has changed enormously in last 10 years. The same time, Facebook, Twitter was implemented, so your customers, your market opinions is changing very frequently. People are more excited to go to this public platform and share. The important thing happened is the invention of Hadoop, which provided us the capability so we can actually analyze the trillions of data, terabytes of data in a distributed 200, 500 node servers and still produce the results in few minutes. The same year, many things happened. GitHub is one of another uh, innovation of that year. If you followed the news, recently Microsoft acquired this company. So as the Airbnb, Intel, cost of DNA changing. So what happened with this in that 10 years before, in that 2007 to 9 time, the power of computing start expanding through clusters and the data. For example, in your aircraft industry, you always had so much of data, but it was not possible to process that amount of data and create tons of the models to find the exact failure, probably one or two, but that never produced the result. And we saw that when we tried this problem back in 2011. But with all this change, the machine learning algorithms start evolving. And if you follow the news, that's the around time in 2011, where IBM invented the Watson solution. That was the IBM's machine learning platform, which competed with one of the two best participants on Jeopardy show and won the show hands down. In that show, IBM Watson could understand the messages the way humans speak, the way you and me speak, and process the natural language. Watson could process that message, understand the meaning, and respond like a human do. Watson that time has processed terabytes of data, trillions of documents, and as soon as the question comes, it can find the right document, right page, right paragraph, which answer that question. That's the capability machine learning is building with understanding the unstructured information and finding the right answer in less than a second probably. So if we want to understand the AI technology, there are four basic principles AI technology should do or is doing today, and the concept we have used for building the predictive maintenance in our solution. The first is it must understand the way humans do, the way you and me understand a message, or we look at aircraft data and we try to find the pattern. The machine should learn in the same way. It should understand the meaning of a text as good as it understands the numbers. 10 years before, machines were very good in understanding the numbers, but it could not process a simple line of text. That problem is today resolved. Machine can understand that information. The second is it should create and extract ideas from the data. It should be able to relate that information and find some reasons from that data. The third is then it should learn from the past. So it should be able to learn and tell us that these are the documents I read, these are the relation I created, and I produce a result, but that is not enough. Traditionally, when we are doing the predictive maintenance or we are writing the models for predicting what will happen, we continuously have to evolve that model ourselves, keep focusing, keep the model up to perform as we need. But in the new machine learning, self-learning, the machine has to learn itself. The way we have learned to learn ourselves, the machine should learn from the past result, understand if there was a mistake and correct in the next iteration. So the results can be improving by itself. The fourth, which is part of the AI technology, probably not for the predictive maintenance, is it should interact in the natural way. So the way you and me speak, the machine should be able to speak to an individual for the communication. So probably that's the area where you see the cognitive computing, or as you know, chatbots coming in, where the machine can interact in the natural way with the humans. So with all these forces, what has happened is now the whole world in various industries has completely changed with the innovation of AI technologies. The first thing is the power of the individual has changed. Now, when I show you the demo on how we are doing the prediction in the end of this session, and we have the sample data, I will show you in action how quickly the technology can read the data, understand the pattern, generate the model, and do the prediction for us in few minutes. What happening is with such technology, we don't need data scientists. We don't need somebody to look into the data, clean for us and everything. We don't need a huge team. An individual from a mobile phone can just upload the data and connect with that. Somebody talking to a chatbot, a single person can interact with chatbot. You don't need a team to interact with that. Of course, still the power of many is important. So now the group of people can come together and innovate a new idea using such a powerful technologies. The power of flows is changing. The opinion
Join the
changes so
meeting.
fast. Opinions are changing so fast. People are talking on the social media. The perception about your company probably changes from morning to evening. A person who posts something on a group, probably the influencer level is high or cloud score is different. He can actually change the whole opinion, and it becomes very important to understand and monitor that kind of data. And last, as I said to you, the power of machine has changed. Now we have machine and sensors which can understand all five senses. It can smell, it can see, it can hear, and it can make the reason from it. And of course, as I said, it can think the way you and me do in just more computing power. So multiplied by 1,000 times, if I can generate a model for predictive maintenance in 1 week, a machine can do probably millions of models. And we'll see that in demo in action. So that's why I say now the future is already here. So time to join with hands with the machine to help them in our solving the solution, which probably were impossible for this huge amount of data or generating so much of models is possible today. And we have solved that problem for some of our customers, and we see in action. So time to join the hands with the machine and future is already here. With that background, I will come to the actual use case on how we are solving the predictive maintenance problem for the aircraft engine as an example. Very quick introduction to the points, what was really lacking or important to solve this problem. The first thing is the data that we needed for the aircraft engine failures and the defect detection. The data is distributed in many systems, in many form and format. The data is in structured databases. It is in different system. FIS data is different, and the weather data is external. Some data, maintenance logs are unstructured. Unless we can join all this information together, it was not possible to solve. Some of the information were external. We have some data from like weather information coming from the web. Some data may be coming from the sensors. Unless we can join all this data together as internal, external, structured and unstructured data, we can't reach to the number of variables or the information which can keep improving the accuracy. Probably we can get 30% with only internal, but that doesn't solve the problem. We need to reach to a place where we can get to 80 to 90% accuracy consistently without writing the code ever again. So that's what we did in the first step is unify all the data. So this AI machine can actually connect to all the sources, understand the reason to connect, and unify the data automatically. The second step is once you can unify, it should understand what that unstructured data means, right? So that's where we have the NLP layer, and system can understand and create variables or, as I said, the reasons from that unstructured data. And third, and equally important, is the self-learning. Then this machine should learn from all this in unified data and the NLP transformed information to produce that accurate predictions automatically for us without even writing a single line of code. So that's how we build our platform. For accurate prediction, why we were lacking that uniqueness in the prediction, and we are working with customers in many industries where we are actually producing 99% accuracy in predicting the sales or for the aircraft maintenance in high 90s. The reason is when I was writing the models earlier myself using a statistical method, it is not possible to generate multiple models. Writing a single model takes few weeks for me, probably a week for you, but that single model does not solve the problem. We learn only one way that a defect can happen or one way that engine may fail, but there are thousands of patterns. The first basic principle, prediction 101, you need to have multiple patterns. The second is we must take as much history as possible. Taking the sample data will have the sampling error. Why we take the sample data? Because the human brain cannot understand terabytes of data. So we start with 10 variables, probably 10,000 rows, and create a model and miss a lot of pattern from our data. And similarly, the third, as I said, many variables. Just the aircraft log is not enough. You have other information in terms of how weather impact, how the pollution impact, how the flight information system log may be useful. We don't know. Unless you combine all this data, and then you can learn how this data is increasing the probability. So that's where we start. That's where the solution is required. We are using that concept and applying the self-learning machine. In last 5 years, we developed this system who takes the input data as the training models and automatically create the models for us. So this self-learning engine can take a simple CSV file or connect to a data source and take the data in the machine and start learning by itself. By learning itself, it can generate the statistical models or the prediction models for us, as many as it finds from the data. So we don't limit to one model or one pattern. Just giving a single file, machine automatically learns and creates thousands of models for us. Once the model is created, now we need to apply that intelligence that machine has learned for creating the prediction. So for predictive maintenance, the finding which machine, which part may have a fault and when it may have fault and what could be the possible solution, right? So that learning is then applied for in the second self-learning engine, which is automatic prediction. So that's where we give the current data. So in training data, you may have given the historic engine log, which some of them failed, some of them not failed, some of them has defect, some of them has not. Machine has learned all the patterns. For defect type A, there could be 100 patterns, machine has learned. For engine failure, there could be 500 ways in the history, machine has learned. Then we give the production data for the current engines, and machine applies each model to each record and see which model has the best pattern for that particular engine. So it can find that engine A is probably likely to fail in next 2 weeks because of tip burn failure. So that's the way it applies each model to each record using unlimited variable, unlimited history, applying the model one by one and selecting the best model. So we are not limiting to best model or single model to all the data. We are actually using best model for each and every record. And this is not possible humanly. Only the machine can learn and apply that complex matching for each record to do the prediction. So now coming to our challenge of predicting engine defect. As you know, though we had a lot of information generated from the flights itself actually, but without the Hadoop as a big data system, clusters, and the self-learning, it was not possible for us to do this kind of prediction. I'm sure in your industry and in your world, you know how critical it is to find the engine defects and more importantly, engine failures in advance for many, many reasons. I don't need to repeat to you, but you must have followed the news and how critical it becomes to detect the engine failure. So in the sample data, and we'll see the demo in next 5-7 minutes, we have already used this AI technology, our Findability platform, to resolve this problem. We have used for B772, Boeing 772 engine, flight, some of them uses GE90 and Rolls 892 engine. Taking the data first from the QAR, flight information system, some pollution data, some weather, and we have planned to add much more data. So as the journey goes, we will add more external data and internal data into the system. So it learns automatically and improve from that 80 to 90% to even higher. Many kind of defects happen in the engine. Some of them, I'm sure you know these defects. Engine may fail because of ball problem or because of tip run through, or there is a blade damage or duct segment is cracked, for many of these reasons, and we have to learn each one of them. Some of them are critical, like tip burn through requires engine removal, but some of them is just corrective action. So probably if the cylinder ball is failed, probably you will fix it, or seal is cracked, it will be replaced. In the data we have taken, what we have seen actually for a single engine, there could be a 300 approximately defect may come every month. Of course, most of them is major or average category, but the maintenance team always has this much of work for each engine. The amount of variables that we have increased is approximately 3,000 variables we are taking for the prediction. So you can just imagine like an Excel sheet, you scroll through 3,000 columns. Probably when I reach to 2,000 column, I won't even remember what was the first one. The machine can learn all of them. When we are doing the prediction, in less than 24 hours, the machine generates 6,000 models approximately. Every week, we take the data and do the prediction. The machine generates 6,000 models. Probably it will take few years for a human, and by the time, the another challenge is, even if we generate 10 models working on for a few months, by the time we put these models for production, the pattern has already changed in the data, probably. So the models is already obsolete by the time we are putting it for production. So not only generating this 6,000 model is important, generating these models and putting to production within few days or in a week or a few weeks is equally important, because the pattern or the reasons of these defect or failure may be changed by the time you spend 6 months to build a two model and try to perfect it. Currently, we are around 78 to 83% accuracy with our system. As I said, we are working to add more data sources and aim to reach to around 92 to 95% while we add more information in the system. The another interesting and important point is, any model we generate for the predictive maintenance, in fact, for any kind of statistical model, whether it's even the customer sales, for example, the models perform decently in the start because that's the time we test and deploy. But if you don't maintain the models, the accuracy start falling. The reason, as I said, the environment changes, variable pattern has changed, and you are using the old algorithm, which is 3 months old. So in fact, actually, you are writing the maintenance for your model to maintain for the predictive maintenance. Here, these models are very stable. Every week, system generates 6,000 models, and maybe next week, it will generate, some of that model may not be there in the last iteration and just generated new, because in this week data, it found some new patterns. So with that, we will directly go to the demo. I'll show you the actual files. We have taken a sample data, a dummy sample data. Of course, we can't share the live information. It's a sample file with a few record. The actual data and the big information will take 24 to 25 hours. It takes every week. But we can show you some sample data and see how that data, even the small part of the data, can give us a good, decent accuracy. So Vivek, I'll stop this screen and I'll switch to my another system.
Okay, Sumit.
Okay, so what you see on the screen is a small sample data for engine aircraft failure, aircraft engine failure. We have approximately 200 variables in this 196 variables in this file. The column C, days left, is what we want to know for current engine. Is how many days left for engine to fail. So can machine learn from the history data from the engine which failed and reading is 30 days before failure log and understand what's the pattern for 30 days failure. And similarly for all other days. Some of the variables you may know already, like takeoff weight of the flight may have a relation. What was the landing weight of the flight? Um, let's see. This is the uh, flight number 773, Boeing 773. Um, what was the plane takeoff weight? What was the onboard fuel? How much distance it traveled? What was the flight distance plan actually? And what was the actual time taken, altitude of the flight, initial cruise altitude, then outcome. So without going to all the variables, there's thrust information, all the what was the pollution at the arrival and departure, all the information that the flight QAR generates, uh, flight information system generates, pollution and weather information all combined as a single file here for the engine. Now the engine generates a log every second. So for every flight, we have around 20,000 to 50,000 logs from each flight. So some of these variable you may find it is repeated, but then some other variable will have a different information. For different days, that's where we can see for there's a different pattern for 26, different for 87 days left, 67, 91, etc. So what is needed in our system? This is the one chaining file we prepare. In the This is the front end of our AI engine, and it can be used, as I said, as simple as from your mobile phone. You can just log into this system and use this training file to upload. So I think login session is expired. So log in again. So what is needed for AI engine to kick is we just need two kind of information. The first, with 5 buttons, we can actually start a new self-learning job where machine can learn. We specify a name, so we engine failure prediction for webinar, and we just give two information. What is the historic data file? What we want machine to learn from? That's our training file. And second is the prediction file. That is what we want machine to apply the learning. So the training file which we saw just now, that we will provide as a training file. We provide a target variable. The another thing is machine can learn create the models based on what we want to predict. Here, we want to predict how many days left for the engine failure. But you can actually use the same data to predict a new column. So if I want to know what will be the takeoff weight of the flight, I can use the same data and can find other variables which impact this. So just changing few parameters, machine can start learning completely in relation to how that value has a relation with everything else, 3,000 variables in your data. And we say unique identifier. So that ID you can take after the prediction, you can actually import the prediction result in your core systems and relate with your actual data. These are only the few things required. I want few minutes to explain to you on the radio button on the top. Very quickly, you can actually ask machine to do both work for you, learn and apply the learning. Or in many cases, customer ask us, like in this case also, the modeling or the learning part happen every week, but the prediction happens every day. So we can separate the job where we ask the learning to happen separately and then apply that learning in the predict part. So model and the predict can be separated as two different jobs rather than a joint job. Of course, for the demo, we will use it jointly. And that's it. We just click on a button and the files will be sent on our AI server and machine will start learning. You will see in few seconds how quickly machine can learn and create the models. So by the time actually humanly I could open the file or start understanding the data, machine can actually generate the model. That's where the self-learning AI becomes critical. You will see on the screen, 82 models is generated. The cluster is scaled by the time I click the button. It optimizes how many servers is needed. It optimizes and distribute the data and it start learning automatically for us. This job is small data. For the training, I have approximately 60 records for machine to learn and for training to predict 30 records. Even this small size, the machine will learn for us. In interest of time, this job will take few minutes. I have a job already in history. I'll show you the result from there and we'll come back and see what is the progress of this job once we see the result and see if that completes as well. So we can actually click on button show job summary to see the historic jobs. So that's a previous job. I use the same data. We'll see the result and come back here. And after that, we can take questions and answers. The system tells you how many models it has generated. In this case, 204 models are generated, 60 records given for prediction. That system is predicted. We can know what are the top variables that are used for the prediction. So the combination of flight time and altitude and fuel flow, these combinedly creates the models for us, which gives us the prediction. The important thing is we can download the full results and we can analyze and see whether what accuracy machine is giving to us, what are models it has generated, which are those models. All this information we can actually see from this report. Okay. So most important part in the report is what system predicted. That's where you can see the prediction result file. Interestingly, you'll notice that the predicted value and the actual value, which was in the file to compare. So if you upload a prediction file with the actual value, machine kicks two processes, the self-learning and the analysis. In the self-learning, it will ignore the actual value, do the prediction, and then compare the prediction and actual to tell us the value. If I just sum on the image, I hope you can see the bottom of the screen. We have 61 record and 55 has matched from this. So if we quickly go here and say and count, we have 91% accuracy. So total record with how many are ones? One means it's a match, and simply 0 means we could not predict accurately. 91% records are predicted accurately in this case. You can see the full log of the system. We ran the modeling plus prediction job, 204 models generated. We had 196 variable, 60 records to predict, and total time is approximately 3 minutes 32 seconds. We will also give you further details about what's a prediction versus actual as a chart. You see the bottom line mostly same because the predicted and actual value is same. In some cases, if it is different, then red and blue dots will be not on the same line. We can also see decile-wise performance. Decile means dividing the data into top probability 10% and then second 10%, etc. You will see in the data the top 3 deciles, which is mostly used in the production for the customer. Top 30% of the data has 100% hit rate. So Even though the overall is 91%, top 3 decile is giving us 100% accuracy and 100% probability. So very, very high confidence, completely accurate results. We can see top models as well as generated, because this is useful in your action. So after the system is predictive, let's say system says engine is going to fail, probably you want to take the next action to investigate or schedule it for the maintenance team. Sometimes these critical variables becomes useful to know what was the variables that system has identified. So probably your maintenance team or people acting on it can make the decision accordingly. What was those variables system identified, and the domain experts can apply their knowledge in how this variable has a relation or connection with which part, and use that to investigate. Summarizing very quickly, let's go back to our job. I want to see the job we started, whether it succeed or it failed. Okay, so it says job completed successfully. So we should have another entry here. Of course, the same job, so we see the same result. Or if you want, you can see the job summary as a predicted versus actual chart here, and see how well system has performed. This is engine failure prediction, so it's comparing the number, but we can actually build the different model, as I said, for different use causes. So it may not need to be one kind of failure. We can actually mix the data where system doesn't predict the number of days only. It can predict the kind of defect as well as when the defect can happen. The most complex part of prediction, and some of the statisticians or data scientists in the room will know, like if you use ARIMA or random forest or something, is making a time series. What will happen and when will happen. That's the beauty or the part of the self-learning machine. It can do both for us and just do it automatically. As you see, in less than 5 minutes, I have generated 200 models. If I write code for even for linear regression or using ARIMA time series, we'll at least need a week or something to create one model and then use another data set for testing. So that's about the AI technology. As I said, Vivek, if we have any questions, we can open for questions and see if I can answer some of them.
Thank you, Sumit, for the presentation. Sumit, as well as the demo. Here we have got one question from one of the attendees. How long does it take for you to get this set up for a new company, Airline?
Vivek, let me understand the question. Question is, how long will it take for the new deployment or new setup for a airline company?
Very true. Yes, you got this. You got the question right.
Right. So the simple answer is, on average, it takes approximately 6 to 8 weeks for a new deployment to go on production with us. But practically it may vary. So how quickly you can give us the data and we can connect to your systems, how you want the result to happen, going back to your systems or seeing in this dashboard or utilize. By the way, this system also have a REST API integrated, so you can utilize the API. So it varies on few factors, how much data we need to process and what use case we need to predict. But on average, standard, it takes around 6 to 8 weeks to go on production.
Thank you a lot, Sumit, for the answer. There's one more question that is coming up that says, can the prediction solution be used for airframe maintenance or airframe prediction?
Used for?
Airframe maintenance prediction.
Oh, absolutely. Absolutely. See, the basic theory is any use case. So we are doing many kind of prediction in many industries. Okay? So we are working with retail to predict what customer will buy and when, how much amount will be sold. Each 15,000 store item, what quantity will be sold. Engine failure we are talking about. The theory is simple. If you have the historic data where, let's say, airframe maintenance, right? If you have the historic data, you can predict what customer will buy and when, how much amount will be sold. Each 15,000 store item, what quantity will be sold. Engine failure we are talking about. The theory is simple. If you have the historic data where, let's say, airframe maintenance, right? historic data where which machine can use to learn, and it should have the mix. It should have some of the failures, some of the success, right? So even the one failure engine for things, right? It has succeed days, it has failed days. So if you have the historic data to give the machine, the way I will write the statistical model myself, right? I'll take some history data and try to create a new model. If you have the history for machine to learn, yes, it's a use case, and machine can learn and do the prediction.
Thank you a lot, Sumit. Sumit, there is one question about the pricing models that you all provide. Can you throw some lights on the pricing model as well as the various implementation model?
Right. So the system is offered into two ways. The first is you can, if you have the data scientist or the statistics capability, and you want to use the system as yourself, you can take it as license model. What you see on the screen, the same thing will be deployed on a dedicated instance for you, and you can use it yourself. That's the first way. The second is full service, where my team will work for you. You don't need to worry about anything. Just either upload the data on FTP server at a regular interval, or allow us a VPN connection, and we can fetch the data from your original or the archive systems. So those are two methods, and in the second full service method, we will do the everything. So we will upload the data, process, and schedule time. You need daily, you need hourly prediction. Everything will be done by us, and we return the result to you. Uh, so the system can use one of these two methods. Pricing actually varies. I cannot give you the definite answers, but pricing is determined by your use case and how much server you require. So platform is offered as a per server license basis. So your use case may require three servers or one server, depending on how complex it is, how frequently you need. If you need prediction once a month, probably you need less servers, versus some of the retail customers are using it every hour prediction, then they need much more servers. The details, probably the costing will be given to you once you talk to Vivek and tell us the use case. We will do the estimate and suggest you that, for example, you need two servers or one server license, and tell you the estimate how much it will cost you per month.
Sumit, there is one more question, okay, that talks about the data required, okay, are at the server. Can you host it on a cloud also?
Yes, so platform is hosted on the cloud. What you see, I'm accessing from the cloud. So your data will come to my platform on the cloud itself. And if your question is, can I connect to a cloud instance? So yes, we can take the data from AWS if your data is on there, or foreign system. See, the only thing I need is it should have either API to give me the data, or connect through VPN and extract the data.
Okay. There are many questions that are flowing in. I'm just going to take the last question. Okay. Now this is related to modeling. Okay. Do you
Okay.
do you use random forest for modeling?
No. So very good question, and thank you for the person who has asked it. We don't use random forest. The system is built with the non-parametric algorithms. It doesn't use any of the traditional random forest or decision tree, or linear regression, or any of those. We have our own proprietary algorithms. We don't force fit the models to the data. We extract model out of the data. So short answer, no, this is not decision tree. We have developed our own proprietary algorithms to learn the patterns from the data and generate the models. Just to for the technical person ask the question, it's a non-parametric based algorithms. So if you know for this, if you know Bayesian classifier, that was the earliest version of how the non-parametric self-learning could have been written. But as you know, Bayesian classifier has its own fault.
Sumit, in the interest of time, we would like to, end the webinar. Should you all have any questions, you can write back to us at vivek@findabilitysciences.com. With this, thank you everyone to attend this webinar. Thank you, Sumit, for giving such a wonderful webinar. Look forward to connecting. Thank you, everyone.